Hello, myself Dr. Anush Purwar. Today I am taking lecture on hydraulic consideration and designing part 1. In waterworks there are two stages in the transportation of water. First is conveyance of water from the source to the treatment plant, and second, conveyance of treated water from the treatment plant to the distribution system. In the first stage, transportation of water is done by gravity or by pumping or by combination of the both, depending upon the relative position of the treatment plant, source of supply, and nature of groundwater. In the second stage, water transmission is done either by pumping into an overhead tank and supplying water by gravity to the user or by pumping directly the mains for distribution. Transportation of water in the waterworks may be divided into two systems: free flow system and pressure flow system. Free flow system, the water in the conveying section flows freely due to gravity, such as flows through the canals, flumes, great aqueduct, great tunnel, etc. In the pressure system, the flow in the conduits is under pressure. Water pressure and Bernoulli's equation. When water is contained in a vessel, it exerts force at all points on the side and bottom of the container. If P is the force acting on an area A, pressure intensity P is equal to capital P divided by the A. The direction of this pressure is always at right angle to the surface with which water comes in contact. Consider a vessel containing some liquid. The water will exert pressure on all sides and bottom of the vessel. Let a cylinder be placed in a liquid as shown in the figure. The weight of the water contained in the cylinder is equal to gamma H into A, where gamma is equal to unit weight of water, H is equal to height of water in the cylinder, and A is equal to area of the cylinder. We are seeing the height H of the water in that figure. The pressure at the bottom of the cylinder will be due to the weight of the liquid contained in the cylinder. The pressure P is equal to weight of liquid in the cylinder divided by the area of the cylinder base. Then is equal to gamma H into A divided by A, then is equal to gamma H. Above equation shows that the intensity of pressure at any point in water is proportional to its depth from the surface. Thus, pressure is expressed in either of the following two ways: as a force per unit area, this is in a unit Newton per meter square, or we can say kilogram per centimeter square, and second as a height of equivalent column of the water. Now Bernoulli's equation. This is V square upon 2G plus P plus Z is equal to constant. Here V square upon 2G, this is the kinetic energy, P is pressure energy, and Z is equal to the potential energy. So in that equation, V is velocity of a unit mass of water, P pressure, and Z height above some given or assumed datum. Above equation can be expressed in words as that the total energy possessed by a unit mass of water is comprised by three parts: its kinetic energy of the movement, its pressure energy, and its potential energy. That is energy due to its position above some given datum in a gravitational field. Equation also states that for an ideal frictionless fluid, the sum total of energy does not change as the mass of water moves from one position to another, so long as no energy is taken away by friction and none added. Since water is not an ideal fluid and when it passes through a pipe, some energy is lost through the friction. A modified form of Bernoulli's equation result which relate the total energy possessed by unit mass of water at two positions A and B measured above a common datum. This is the in figure. We have taken the point A and B. Water is input as a point A, and this is we are showing here a figure is output at point B, and all details regarding the kinetic energy, pressure energy and datum energy is shown in that figure, and here the energy line for per unit mass of the water also shown in the that figure. So now equation we can write as VA square upon 2G plus PA plus ZA. All these energy contained in the point A is equal to VB square upon 2G plus PV plus ZB. All energy contained in point B plus energy loss, where HF is the energy lost through the friction as the unit mass of the water moves from position A to B. Now flow through open channel. An open channel is a passage through which the water flows under atmospheric pressure or when the free surface of the flowing water is in contact with the atmosphere, as in case of canals, a sewer or an aqueduct. A channel is mostly open, but it may be covered at the top in special cases. In that cases, principle of open channel flow will only apply when they are not flowing under pressure and water does not flow in full section. The flow of water in an open channel is not due to any pressure as in case of the pipe flow. It is due to the slope of the bed of a channel. Although the velocity of flow is different at different points in the cross section of a channel, all calculations are based on the mean velocity of the flow. Further, the velocity of the flow is assumed to be steady and uniform. For analysis, the rate of discharge, depth of flow, velocity, slope of bed and cross-section area are kept constant over a given length of the channel. So here the discharge, now discharge through an open channel. This is the Chase's formula. So here we considered a open channel of uniform cross section of the length L as shown in the figure. So let's consider L is equal to length of the channel, A area of the flow, V velocity of water, P weighted parameter of the cross section, F frictional resistance per unit area at unit velocity, I uniform slope in the bed, and small l the length covered by water flow per unit time. So frictional resistance is equal to F into contact area into velocity की power n. So is equal to F into P into small l into V की power n. The value of n has been experimentally found to be nearly equal to the 2. So put the value of n is equal to 2 here. So frictional resistance is equal to F into P into L into V square. Since water moves through a distance V in 1 second, hence work done in overcoming the friction is equal to frictional resistance into distance is equal to F into P into L into V square into V. So is equal to F into P small l into V cube. Weight of water in the channel in the length of L meter is equal to gamma A into L. Here W is equal to specific weight of the water. So this water falls vertically down by a distance equal to V into I in 1 second. So we can say loss of potential energy is equal to weight of water into height is equal to W small w into A into small l into V into I. इसलिए वर्क डन इन ओवरकमिंग फ्रिक्शन इज इक्वल टू लॉस ऑफ पोटेंशियल एनर्जी देन F into P into L into V cube is equal to gamma A L V into I. So we can calculate here from here V square is equal to W A I upon F P. V is equal to root gamma upon F into root A upon P into I is equal to C into root M into I, where we C is equal to, we can say, a root gamma upon F. This is the known changes constant. M is equal to A upon P, known as hydraulic mean depth. So discharge is equal to Q into A into V is equal to A C into root M I. The value of changes constant C depends on roughness of the inside surface of the channel. Scientists have conducted a series of experiments and proposed relation for the values of C in the changes formula, out of which following relations are important. First is Cutter's formula and second is Manning's formula. So in Cutter formula, C is equal to 23 plus 0.00155 divided by I plus 1 by capital N, and whole division by 1 plus in bracket 23 plus 0.00155 divided by I bracket close into N divided by root M, where N is the constant known as Cutter's constant, whose value depends on roughness of the channel surface as given in the next table. I is the bed slope and M the hydraulic mean depth. So here is the value of the capital N in the Cutter formula. Smooth, if there is a smooth cement plaster, then value is equal to N is equal to 0.01. In case concrete or unplanned wood, then value of N is equal to 0.012. Poor brick or rubber stone, 0.017. In case of earth of very good surface, value of N is equal to 0.0020. Earth of ordinary surface, then value of N is equal to 0.025. If surface is rough, earth of rough surface, then value of N is equal to 0.030. Now Manning's formula for discharge. Here C is equal to 1 by capital N into M की power 1 by 6 for the constant C. So here N is equal to, we can say again Cutter's constant and the same value as we can get from the table. So now velocity V is equal to C into root Mi is equal to 1 by N into M की power 1 by 6 into root Mi. So is on simplification it comes M into capital M into small m की power 2 by 3 into I की power 1 by 2. Here capital M is equal to 1 by N. This is known as the Manning constant. So discharge Q is equal to area into velocity is equal to A into capital M into small m की power 2 by 3 into I की power 1 by 2. Channels of most economical cross section. A channel of most economical cross section is that which gives maximum discharge for a given cross sectional area and bed slope. In other words, we can say it is the channel which involves lesser excavation for a design amount of the discharge. While deriving the condition for a channel of most economical cross section, the cross section area is assumed to be constant and a relation between depth and breadth of the section is found out to derive maximum discharge. For waterworks, mostly trapezoidal section of channel is used for carrying water, but sometimes a rectangular section is also used. Hence the condition for maximum discharge will be dealt for rectangular section and trapezoidal section. So first we will see for the rectangular section. Consider a channel of rectangular section as shown in the figure. This is the depth D and width of the B. So discharge is equal to Q is equal to A into V is equal to A into C into root Mi is equal to A into C root A by P into I. Here A, C and I we can keep the constant, so discharge will be maximum when A upon P is maximum, or we can say parameter P is the minimum. So we calculate solve the equation for the minimum of the P. So dP upon d is equal to then 0, because P is equal to B plus 2D is equal to A by D plus 2D. So differentiate in this terms, so we can get the for the optimum value is equal to dP by divided by dd is equal to 0. So A cap is equal to 2D square, or we can say B is equal to 2D. So when breadth is equal to double the depth, and in this case the hydraulic mean depth is m is equal to A upon P is equal to D by 2. So for maximum discharge or maximum velocity, B is equal to 2D, or and M is equal to D by 2. Now trapezoidal section. Consider a channel of trapezoidal cross section ABCD as shown in the figure. Here the bottommost width is B, and the slope 1:n, and total depth is equal to D. So area of the flow A is equal to D into B plus ND. So discharge Q is equal to, on simplification, AC into root A by P into I. So again here we keep the A, C and I constant. So for the maximum when A by P is maximum, or discharge will be maximum when A by P is maximum, or parameter P is the minimum. So again differentiate dP upon dd for the is equal to 0. So we get the, in that terms we get the P is equal to B plus 2 into root n square d square plus d square. On simplification is equal to B plus 2d into root n square plus 1. We keep the value of B in equation, so we get the P is equal to A by D minus ND plus 2D into root n square plus 1. So here on differentiating we get the value B plus 2ND divided by 2 is equal to D root n square plus 1. So we can say the sloping side on AB or CD is equal to half of the top width. So for such condition, hydraulic means that M is equal to A by P is equal to D by 2. Hence, for maximum discharge or maximum velocity through a trapezoidal channel, following two conditions should be used. B plus 2 and D upon 2 is equal to D into root n square plus 1, and M is equal to D by 2. Now circular section. Circular section are not so common. They are used in sewer and sometime in tunnel when a discharge has to pass through such terrain. In case of circular section, maximum discharge take place when the depth of water is 0.95 times the diameter of the circular channel. Here are the few examples based on these calculations. First, a water passage of rectangular cross section is to carry 12 cubic meter per second of water at a velocity of 2.5 meter per second. Design the most economical section. Take changes constant at 50. Also calculate the necessary slope for the bed of the channel. Now area A is equal to Q upon V is equal to 4.8 meter square. For the most economical rectangle section, we know B is equal to 2D. So area is equal to 2D square. So 2D square is equal to 4.8. Now we calculate that D is equal to 1.55 meter. And then width is equal to B is equal to 2D is equal to 3.1 meter. Now bed slope. Let I is equal to bed slope. Then For the most economical rectangular section, hydraulic mean depth is equal to m is equal to d by 2 is equal to 0.775 meter. V is equal to c into root mi. So put the all value here. V is equal to 2.5, c is equal to 50, and m is equal to 0.775. So we calculate the I is equal to 1:310. So bed slope is equal to 1 in 310. Now second example, design an earthen trapezoidal channel with velocity of flow 1 meter per second and to discharge 3 meter cube per second and having side slope 1 in 2. Take C, constant C is equal to 55. Now again area A is equal to 3 meter square. For design the most economical section, M is equal to D by 2. So and parameter P is equal to B plus 2D into root and square plus 1. So put the all value here. So hydraulic mean depth M is equal to A upon P is equal to D upon 2. So we got the equation BD square plus 4.472 D square plus 6. For the trapezoidal section, area is given. So we find the value in terms of the BD is equal to 3 minus 2D square. So value of put the value of BD in equation. So we got the D is equal to 1.1. Putting the values, then we got the B is equal to 0.53 meter. Now slope of the channel bed. Let I slope of the channel bed. Then V is equal to C into root mi. Put all the value here. V is equal to 1, C is equal to 55 into root m. Put the 1.1 divided by 2 and we have to find the I. So I comes the 1 ratio 670. Now another example, a brick-lined trapezoidal canal has side slope of 1.5 horizontal to 1 vertical. It is to carry water at the rate of 50 cube max. If the average velocity of flow is not to exceed 1 meter per second, find the weighted parameter for minimum amount of lining and bed slope assuming Manning's constant n is equal to 0.015. Now solution, for minimum amount of lining the section has to be treated as the most economical one. For a most economical trapezoidal section, half of the top width is equal to sloping side. So put all the values, we find the relation B is equal to 0.6 D. Because A is equal to Q upon V, then put the value of A, put the and this is equal to the D into B plus ND, and put the value of the here A. So we get the D is equal to 2.66 meter. So we in that case B is equal to 0.6 D is equal to 1.6 meter. Now weighted parameter P is equal to B plus 2D into root n square plus 1. Put all the values here. We get the P, capital P or weighted parameter is equal to 11.2 meter. Now bed slope. In case of most economical trapezoidal section, hydraulic mean depth M is equal to D by 2 is equal to 2.66 divided by 2 is equal to 1.33 meter. Now for the Manning formula, V is equal to 1 by n m की power 2 by 3 into I 1 by 2. So put the value V is equal to 1, n is equal to 0.015, m 1.33, and we have to calculate the I. So now get the value on solving this equation. I is equal to 1 divided by the 6500. So this is all about the hydraulic consideration part 1. Thank you.